Welcome to TalkCast, and what is episode 199 of TalkCast. At least kind of. The numbering system applies to the audio-only version of the podcast, and unfortunately, the ordering there, it's recently been brought to my attention, is out of whack. It's out of line with what appears on YouTube. In particular, there's one episode that I failed to transport from YouTube over to the audio platforms, which means this is really episode 200. It's just that I haven't yet put the audio version of that missing episode onto the audio platforms yet. So this is going to appear in feeds as episode 199. And as I've already promised, there will be something different and special for episode 200. So that missing episode, a little bit of TalkCast trivia, is going to appear completely out of order, likely as episode 201. Okay, so as Sam Harris would say, that's housekeeping out of the way. Today we continue with the discussion of one of my favourite chapters in all of the Fabric of Reality, Chapter 10, The Nature of Mathematics. And last time we got through very little reading indeed, because so much of that chapter has been discussed before when I've talked about the mathematician's misconception, Chapter 5 at the beginning of infinity, the reality of abstractions, and a lot of that comes to bear on what appears here in its first, most primitive form in Chapter 10 of the Fabric of Reality. Mathematics is, of course, an unusual subject. Culturally, even to today, it's an unusual subject in the way it is regarded. It has this mystique. Either you understand something about mathematics or you don't. And the less you understand about mathematics, the more you kind of regard, at least some people do, the more you kind of regard those who are more and more proficient in mathematics as having a secret kind of knowledge, secret insight into the workings of the world, something that you are completely blind to. It's almost like the priesthood. It's almost like the ancients regarded their holy men and women, as if they had some special access to a realm that mere mortals weren't able to access, that the usual methods of thinking and reasoning simply didn't apply in this particular realm. And many people are put off mathematics very early on. It's one of those things that children are forced to do, and it also happens to be one of those things for which you are punished if you do poorly at. And so if you make mistakes, well, it's a big deal. It's an error, and errors are not treated particularly well in the schooling system. The only way to learn, of course, is via trial and error, conjecture and refutation. We all make mistakes when we do mathematics, but mathematics teachers in particular are often, let's face it, cruel. They're getting better, but still they're dealing with a subject which, by its very nature, for almost all people all the time, is dry. And they seem to keep doing things in the mathematics curriculum to make it ever more dry, even for the kids that quite enjoy mathematics. For example, when I was teaching and even when I was learning, I enjoyed mathematics, except when they started putting dollar signs in front of things, when we had to calculate the amount of interest that you'd earn over 30 years on a particular loan, how compound interest works, and goodness knows what else. But as soon as those dollar signs appeared, I thought, well, this is boring. I was never Firstly, I thought that the mathematics that was being taught was trivial. It's like, well, of course, this is the same kind of stuff. It's still just arithmetic and multiplication and exponentials. Nothing has changed. You're just putting dollar signs there. But now the questions are more boring about how much money you're going to have after a certain amount of time investing it at a particular fixed rate and so on. And of course, when you do encounter a part of mathematics at school that you quite enjoy, you can't pursue it very far because they introduce another topic that you're not quite so interested in. You happen to find calculus quite interesting? Forget about it for a while. We're moving on to circle geometry. And this is what would happen as you move through senior school, for example. And mathematics, more than any other subject at school, I would argue, having both been a student like absolutely everyone else, and also having been a teacher, is the most competitive of all the subjects at school. It's the one where you really decide who's the smartest kid at school. It's the kid who does best at the highest levels of mathematics. And everyone else is judged in comparison to them. They're the ones that are given the greatest praise and the most valuable rewards, and are, of course, promised the greatest success upon graduation, because their mathematics skills will open up doors to absolutely everything. Well, yes, of course, it's useful to have mathematics. I quite enjoy mathematics, but there's a limit. And I think everyone who takes on mathematics realizes at some point, except for the extreme cream of the crop fields medal winner type people, that there's always going to be someone better. It's kind of like gymnastics. Everyone can give it a go, but you can recognize that there are truly spectacular performers out there, people doing things that you think you could never possibly do. Or if you could possibly do it, it would just take too much effort to get there. It's the hard slog of learning to do a routine on the pommel horse is too difficult. Learning how to do the crucifix on the rings too difficult. It's possible, but who could be bothered putting in so much effort? Well, gymnasts, of course. And so too with mathematics. People can learn this stuff. It's just, well, why? This was my feeling anyway as a physics student. I wanted to know the mathematics that was going to help me do the physics stuff that I needed to do. And the rest of it, well, some of it was sometimes interesting, some of the time. I quite liked formal logic, which didn't seem to have much application to almost anything, except in computer science. But then, of course, I had to take a whole bunch of things that I didn't really want to do, and this turned me off mathematics, and it made it boring. And so I think a lot of science students encounter this. I think one of the greatest complaints from psychology students is the amount of statistics that they have to learn. Because, of course, in psychology, the measure of a scientific study in psychology is how large your sample size is. Never mind the explanations. Do you have data in order to draw a graph so you can reach some conclusion that you've already assumed somewhere at the outset, no doubt? But whatever the case, mathematicians as a profession have an allure that is equalled only by certain physicists, perhaps theoretical physicists, and the only other kind of people who have this allure are priests. The people that you go to for deep insight about the nature of ultimate reality, that kind of thing. And as I've mentioned before on this podcast, it's an unusual kind of impulse that our culture happens to have at the moment, that on important moral and indeed international questions about the nature of artificial intelligence versus artificial general intelligence, policy about warfare and thermonuclear devices. All of this stuff is often referred to the physicist for opinion, and now and again the mathematician. But as we will see in this chapter early on, I've only read a little so far in part 1. In part 2, we're going to get to something like intuitionism. And you'll see here that there is, I would say, a poverty of understanding philosophy at the root of something like intuitionism, something that at least some proportion of mathematicians subscribe to. Mathematics and being proficient at mathematics does not confer upon you the capacity to necessarily have knowledge in any other domain. You have to understand those other domains in their own terms. Okay, let me not delay any further and go straight into the reading of the book. I ended last episode on chapter 10, The Nature of Mathematics, where David was talking about how we are to regard abstract entities like numbers. If they are real, then they need to be part of our understanding of the fabric of reality. But how can we know they are real? What's our criterion? Well, David's about to explain. So let me pick it up where he says on page 222, if you happen to be reading along, quote, "This suggests we ought to apply Dr. Johnson's criterion again. If we want to know whether a given abstraction really exists, we should ask whether it kicks back in a complex autonomous way." End quote. Pausing there. Just so this notion of kicks back in a complex autonomous way means that something unexpected might happen. It has a reality in the sense that you set up the rules of the system, or you come to understand the fundamentals, and then from those fundamentals, emergent structure arises that you can study, and you find that it has a richness, and it's complex, it's autonomous in the sense that you can't just yourself invent things like what a prime number is. That falls out of your assumptions of what mathematics is, for example, which is exactly the point David's about to make. So he goes on to say, for example, mathematicians characterize the natural numbers, 1, 2, 3, etc., in the first instance through a precise definition, such as 1 is a natural number. Each natural number has precisely one successor, which is also a natural number. 1 is not the successor of any natural number. Two natural numbers with the same successor are the same. Such definitions are attempts to express abstractly the intuitive physical notion of successive amounts of a discrete quantity. More precisely, as I explained in the previous chapter, that notion is really quantum mechanical. The operations of arithmetic, such as multiplication and addition, and further concepts, such as that of a prime number, are then defined with reference to the natural numbers. But having created abstract natural numbers through that definition, and having understood them through that intuition, we find that there is a lot more that we still do not understand about them. The definition of a prime number fixes once and for all which numbers are primes and which are not, but the understanding of which numbers are prime, for instance, how prime numbers are distributed on very large scales, how clumped they are, how random they are, and why, involves a wealth of new insights and new explanations. Indeed, it turns out that number theory is a whole world, that term is often used, in itself. To understand numbers more fully, we have to define many new classes of abstract entities and postulate many new structures and connections among those structures. We find that some of these abstract structures are related to other intuitions that we already had, but which on the face of it had nothing to do with numbers, such as symmetry, rotation, the continuum, sets, infinity, and many more. Thus, abstract mathematical entities we think we are familiar with can nevertheless surprise or disappoint us. They can pop up unexpectedly in new guises or disguises. They can be inexplicable and then later conform to a new explanation. So they are complex and autonomous, and therefore, by Dr. Johnson's criterion, we must conclude that they are real. Since we cannot understand them either as being part of ourselves or as being part of something else that we already understand, but we can understand them as independent entities, we must conclude they are real independent entities, end quote. Good. Okay, so being real and existing, I would say, are very similar things. And one way of talking about Dr. Johnson's criterion, and I think this more fully comes out of the beginning of infinity, is do these things appear in our best explanations? And is any explanation ruined by denying their existence? Is any explanation improved by denying their existence? This kind of thing. We say, for example, that if you try and invoke the existence of ghosts, then you violate all sorts of laws of physics. I mean, if this ghost is a thing that requires energy in order to move around, if it's here in the physical world, then where's the energy coming from? What's its energy source? How does it undergo locomotion from one place to another? That's a mystery. That kind of cries out for an answer. And absent an explanation, if you're violating laws of physics, then you're not real. You don't exist. You don't exist because no explanation is required. No good explanation is required in order to explain you. In fact, postulating the existence of a ghost ruins a whole bunch of explanations. It stands in defiance of a bunch of explanations. There are many, many experiments, on the other hand, that attest to the existence of electrons. And when you get to the entire grand theory of the standard model of particle physics, what you then have is the necessity of the electron. The electron exists because it is required to exist by this deep explanation about what matter consists of, what forces are, all this kind of stuff. So this is why we think and say the electron exists. But on the other hand, there is no deep theory of ghosts or theory of anything that requires us to invoke the existence of ghosts or unicorns or dragons or any imaginary thing like that. But with numbers, they are required. Our explanations of physics and chemistry, our explanations of mathematics itself, require that these natural numbers exist. No explanation is improved by denying their existence, but every good explanation, especially in the physical sciences, as well as in mathematics itself, requires their existence. And so this is why we say they exist. Something exists insofar as it features in our best explanations. That's it. And when I say something exists, what I mean is we know that something exists. What else could I mean? I can't talk in terms of ultimate truth or anything like that. All I can say is what we know now. What we know now exists. Is there more than what we know now exists that really exists out there? Yes, but we can't talk about that because we don't know about it yet. There may be alien intelligence out there somewhere or other. But at the moment, no theory requires us to postulate alien intelligence out there. Our present theories allow for the possibility, but don't require that intelligent life be out there. One day, those theories might, especially if we are visited. We haven't been visited yet, though. At least there is no good explanation that requires us to think that we've been visited, and so on. David goes on. Nevertheless, abstract entities are intangible. They do not kick back physically in the sense that a stone does, so experiment and observation cannot quite play the same role in mathematics as they do in science. In mathematics, proof plays that role. Dr. Johnson's stone kicked back by making his foot rebound. Prime numbers kick back when we prove something unexpected about them, especially if we can go on to explain it too. In the traditional view, the crucial difference between proof and experiment is that proof makes no reference to the physical world. We can perform a proof in the privacy of our own minds, or we can perform a proof trapped inside a virtual reality generator rendering the wrong physics. Provided only that we follow the rules of mathematical inference, we should come up with the same answer as anyone else. And again, the prevailing view is that apart from the possibility of making blunders, when we have proved something, we know with absolute certainty that it is true. End quote. And long-time listeners, fans of David Deutsch, and others who've been listening to this podcast intermittently will know that this is something that stands in stark contrast to one of our deep foundational claims about the nature of reality, which is fallibilism. This idea that error is everywhere, that we can always make mistakes. So this canard of absolute certainty is forever going to elude us, but it's never required. And we shouldn't be disappointed that we can't get to absolute certainty either. After all, absolute certainty is a kind of end in itself, the end of progress in a sense. Better to always have uncertainty, the possibility of correcting an error and coming to a deeper understanding of something. That's the truly optimistic idea, even about mathematics. But it's true, even to today, the overwhelming majority of mathematics professors, teachers, and students of mathematics will think that mathematics stands apart in being able to reach absolutely certain truth. As David goes on to say, quote, mathematicians are rather proud of this absolute certainty, and scientists tend to be a little envious of it. For in science, there is no way of being certain of any proposition. However well one's theories explain existing observations, at any moment, someone may make a new, inexplicable observation that casts doubt on the whole of the current explanatory structure. Worse, someone may reach a better understanding that explains not only all existing observations, but also why the previous explanations seem to work, but are nevertheless quite wrong. Galileo, for instance, found a new explanation of the age-old observation that the ground beneath our feet is at rest, an explanation that involved the ground actually moving. Virtual reality, which can make one environment seem to be another, underlines the fact that when observation is the ultimate arbiter between theories, there can never be any certainty that an existing explanation, however obvious, is even remotely true. But when proof is the arbiter, it is supposed there can be certainty, end quote. So here is this hierarchy that rears its head. The hierarchy of mathematics with its absolute certainty, science with something less than certain, and then ideas about all of this stuff, namely philosophy, as being mere matter of opinion. And David will come to that in this chapter. This notion of proof, which David is about to drive a horse and carriages through in this chapter, is often mistaken as being a method for showing something as true. But that's never been the case. And even when I was taught logic at university in a formal sense, at least there the philosophers and even the mathematical logicians would say, we're not proving these things true. We're not proving the conclusion true. What we're doing is assuming that the premises or the axioms, the starting points are true. Assuming they're true, then a valid proof will lead to a true conclusion. But that's a lot of ifs, right? If the axioms, if you're starting suppositions, premises, whatever you want to call them, if they're true, and the rules of inference that you use, the laws of mathematics, if you like, that you follow are themselves also absolutely certainly true and inerrant, then if you make no mistakes along the way, you will get truth at the end. But none of this is guaranteed. That assumes that that whole structure there is hermetically sealed off from the possibility of error, an impossibility. But David's going to get to that. So let's keep going. David says, quote, "It is said that the rules of logic were first formulated in the hope that they would provide an impartial and infallible method of resolving all disputes. This hope can never be fulfilled. The study of logic itself revealed that the scope of logical deduction as a means of discovering the truth is severely limited. Given substantive assumptions about the world, one can deduce conclusions, but the conclusions are no more secure than the assumptions. The only propositions that logic can prove without recourse to assumptions are tautologies. Statements such as, all planets are planets, which assert nothing. In particular, all substantive questions of science lie outside the domain in which logic alone can settle disputes. But mathematics, it is supposed, lies inside that domain. Thus, mathematicians seek absolute but abstract truth, while scientists console themselves with the thought that they can gain substantive and useful knowledge of the physical world. But they must accept that this knowledge comes without guarantees. It is forever tentative, forever fallible. The idea that science is characterized by induction, a method of justification which is supposed to be a slightly fallible analogue of logical deduction, is an attempt to make the best of this perceived second-class status of scientific knowledge. Instead of deductively justified certainties, perhaps we can make do with inductively justified near certainties, end quote. Yes, the poor scientists have to just make do with inductively justified near certainties. But of course, as you'll know, if you follow the work of David Deutsch, if you are Popperian, if you have been listening to this podcast, you will know that all of that is just nonsense. This way of thinking about the world, thinking in terms of certainties and induction, rather than conjectured or guessed explanations of the world. This is really what's going on. And we need not start at any kind of foundation in order to deduce our way to the answer to some problem we have. We can start anywhere. We can start in the middle. We can start at the end by assuming this is the theory and then testing the theory against reality. There are all sorts of ways in which to solve our problems, to come up with explanations and make progress. But ever since Euclid, who came up with these early deductive systems of mathematics, which solved deep problems and were very interesting and very helpful for people. The geometry is a wonderful part of mathematics where you can see, almost every student goes through this and learns, how starting with basic assumptions, you can reach some really counterintuitive conclusions. This whole point about justifying things, it rests upon the idea that what we're really after is not so much explanations, but a truth to defend. That once you have justification for what it is that you believe, then if you are challenged by someone, you can say, I am justified in my belief because of the evidence, or I am justified in my belief because of the mathematical proof, and so on and so forth. Rather than saying, hey, this thing solves the problem, this allows us to make progress, this is the thing that tells us why nuclear energy happens to be safe. We don't need a justification. What we need is the best available explanation. And once we have the best available explanation, it needs no further justification. It just needs no viable rivals. And if it has viable rivals, then we've got some thinking to do and possibly some experimentation. But at no point do we need to fall back upon the justification. We just say, this is the explanation. This is it. This is all we have. So inductively justifying stuff in science was always a fool's errand. Well, okay, so long ago, people didn't know much stuff, but now we know better. At least some of us do. People who are Bayesian are still trying to say, well, we need to put a number on how confident we are with our assumptions or how confident we are with our theories. But it never needs to be done, because if you have an explanation, you have an explanation, and it solves your problem. You just talk about the explanation. If you don't have an explanation, you say, I don't know the answer to this. Here are some candidates. Do we need to rank them? No, we can talk about them in their own terms. We can use conjecture and refutation, argument, in order to criticize, use the critical method, which is what happens in real life, of course. You never see astrophysicists arguing Bayesian confidence levels with each other about their favoured dark matter models. What they do is they talk about the dark matter models and problems with them. You know, someone says, well, I think Marcho's explaining massive compact halo objects. These are these planets, like all the small stars that might be in the halos of galaxies. That's the dark matter. And then a whole bunch of people come along and say, well, if that was true, then we should be able to see them with present telescope technology. And so other people come up with, WIMPs, weakly interacting massive particles. And others say, well, we should have detected these things at the Large Hadron Collider. And so this is a criticism. They don't talk in terms of Bayesian confidence levels. That's just another canard. It's another false representation of what really goes on when scientists engage in proper scientific discussion about potential solutions to known problems. So we don't need to justify things. We need to explain the phenomena which is problematic at any given time. David goes on to say, quote, as I have said, there is no such method of justification as induction. The idea of reasoning one's way to near certainty in science is a myth. How could I prove with near certainty that a wonderful new theory of physics overturning my most unquestioned assumptions about reality will not be published tomorrow? Or that I am not inside a virtual reality generator? But all of this is not to say that scientific knowledge is indeed second class, for the idea that mathematics yields certainties is a myth too, end quote. And that's wonderful. Yes, this idea that mathematics yields certainties is itself a myth. And I like to use the example of, by the way, this idea of, how do you know that a wonderful new theory of physics won't appear tomorrow to overturn your favourite idea today? You never know that. And this is why, again, if I can pick on Bayesianism once again, even though it's not even relevant to this chapter, but I've always thought to myself, if you were a Bayesian back in 1850, then all of the accumulated evidence thus far over the previous sort of 2 centuries had been pointing at the fact that Newton's theory of gravity was absolutely true. You'd be asymptotically approaching 100% confidence, wouldn't you, that this is the theory of gravity? There can be no rival. All the experiments attest to, conform with Newton's predictions, or predictions from Newton's theory of gravity. And of course, that process only continued. It continued to be the case that almost all observations conformed with what Newton's theory of gravity predicted would happen or should happen under any given circumstance, until cracks began to appear. But even then, people would hold out. I often talk about the precession in the orbit of Mercury as being a problem. It wasn't conforming to what Newton's theory of gravity said, but for a long time people presumed there was going to be another planet on the other side of the sun, that we could never see because it was on the other side of the sun, orbiting at the same distance as the Earth did. I think they called it Vulcan or something. And this planet explained why Mercury's orbit wasn't conforming to what Newton's theory said. So even then we had holdouts. But whatever the case, right up until, the day before Eddington's experiment was actually performed, wouldn't Newton's theory have had the highest Bayesian confidence that it could have? But this has never made any sense to me, that the accumulation of evidence, increasing your confidence that this is the correct theory, is always at a maximum. Your confidence is at a maximum immediately before the theory is shown to be false, because all of the evidence has accumulated to the theory that actually is falsified the next day by an experiment ruling it out in favor of the better theory. But we're here talking about mathematics. So the idea that mathematics yields certainties is a myth too, says David. And so he goes on, quote, "Since ancient times, the idea that mathematical knowledge has a privileged status has often been associated with the idea that some abstract entities, at least, are not merely part of the fabric of reality, but are even more real than the physical world. Pythagoras believed that regularities in nature are the expression of mathematical relationships between natural numbers. All things are numbers was the slogan. This was not quite meant literally, but Plato went further and effectively denied that the physical world is real at all. He regarded our apparent experiences of it as worthless or misleading and argued that the physical objects and phenomena we perceive are merely shadows or imperfect imitations of their ideal essences, forms or ideas, which exist in a separate realm that is the true reality. In that realm, there exist, among other things, the forms of pure numbers, such as 1, 2, 3, etc., and the forms of mathematical operations, such as addition and multiplication. We may perceive some shadows of these forms, as when we place an apple on the table, and then another apple, and then see that there are two apples, but the apples exhibit oneness and two-ness, and for that matter, appleness, only imperfectly. They are not perfectly identical, so there are never really two of anything on the table. It might be objected that the number 2 could also be represented by there being two different things on the table, but such a representation is still imperfect because we must then admit that there are cells that have fallen from the apples and dust and air on the table as well. Unlike Pythagoras, Plato had no particular axe to grind about the natural numbers. His reality contains the forms of all concepts. For example, it contained the form of a perfect circle. The circles we experience are never really circles. They are not perfectly round nor perfectly planar. They have a finite thickness and so on. All of them are imperfect. Plato then pointed out a problem. Given all this earthly imperfection, and he could have added, given our imperfect sensory access to earthly circles, how can we possibly know what we know about real perfect circles? Evidently, we do know about them, but how? Where did Euclid obtain the knowledge of geometry which he expressed in his famous axioms when no genuine circles, points or straight lines were available to him? Where does the certainty of a mathematical proof come from if no one can perceive the abstract entities that the proof refers to? Plato's answer was that we do not obtain our knowledge of such things from this world of shadow and illusion. Instead, we obtain it directly from the real world of forms itself. We have perfect inborn knowledge of that world, which is, he suggests, forgotten at birth and then obscured by layers of errors caused by trusting our senses. But reality can be remembered through the diligent application of reason, which then yields the absolute certainty that experience can never provide. End quote. So if you go here to my series on the sources of knowledge and of ignorance by Karl Popper, which is the first sort of few chapters of his book, Conjectures and Reputations, he talks specifically about this idea that Plato had of amnesis, it's called, of us forgetting the perfection of the world of forms and gradually coming to remember some of it over time. It's kind of an inverse, the way that David has explained it there, of what I've often thought of as the reason why people struggle to learn as well later on in life. Many people put this down to, well, the physical hardware of your brain is degrading. So your memory's getting worse, you're thinking more slowly. In other words, your RAM or hard drive is degrading and your processor is also slowing down. Okay, so maybe that's a factor in some cases, but I don't think it's the major factor. Once people start to get above 30, 40, 50, the majority, struggle to do new things. Look at me. I struggle to try and learn new languages, even though I'd like to. I've got a partner who learns new languages, is polyglot, but I am not. I'm the exact opposite. So what makes the difference? Well, I don't think it's a difference in brain structure. It's certainly a difference in interest. But moreover, my own theory is that you just begin to build up a whole bunch of bad memes, some of which are anti-rational. You fear to make errors. You are born, what you have inborn knowledge of, you have inborn knowledge of how to learn, how to conjecture ideas about the world. And young children learn so fast because they are unencumbered early on by lots of anti-rational memes. They're not afraid or embarrassed about making mistakes. They have no fear of being punished for trying something and failing. All of this stuff has to be learned. The fear of learning has to be learned. The fear of making mistakes, the fear of looking a fool, all of that kind of stuff is the obscuring of layers of errors caused by trusting authorities, I would say. So all of that I've just read there can kind of be massaged into our circumstance as entities that learn, but become worse at learning for many of us over time. Some people manage to avoid this, at least to some extent. You look at someone like Richard Feynman and his story, and he just continued to learn, for as long as he lived. He was just passionately curious about stuff, which is what we should want to try and maintain. And not be afraid of trying new things. But of course, many people do become afraid of trying new things. And even though I know I shouldn't, still there's something there in me that prevents me from trying some new things sometimes. I think I'm better than most, but it's certainly obvious out there in the world that the older people get, the slower they get at learning new things, especially things like technology, for example. Now, why? I don't think it's anything to do with the brain. I think it's everything to do with the mind and the attitude you bring to this new thing. A lot of older people think they just can't be bothered. They've learned some stuff, and they could also be discerning, I guess. Taste and preference is a real thing. And so you can more readily realize what you're going to find fun. And perhaps it's just not fun to learn how to, use a new piece of technology, for example. That might be a factor. And so everyone has the old trope of trying to teach their, grandmother how to use a smartphone or something like that. It can be frustrating, but, she isn't so much interested in that. And fair enough. She has her own interests. People become discerning. And that young person with the smartphone, when they get older, will also have their own interests. That's a factor as well. But I think the overriding factor is people are afraid to look a fool. And so an older person is more reluctant to take on new technology as it comes out because they just don't want to seem like they're making mistakes. And they get bored of it. And who can blame them, given the way that so many human beings are still taught today, punished for making errors when they should be rewarded for having a go. Okay, so let's go back. David has just talked about how, we've got inborn knowledge of the perfect world of forms, but it's obscured by layers of errors over time by trusting our senses, and we shouldn't trust our senses. Our senses mislead us. So this is like the opposite to the empiricists, right? Trust your senses. They won't mislead you. Plato's gone in the other direction. Never trust your senses. They'll always mislead you. David goes on to say about this, quote, I wonder whether anyone has ever believed this rather rickety fantasy, including Plato himself, who was, after all, a very competent philosopher, who believed in telling ennobling lies to the public. However, the problem he posed of how we can possibly have knowledge let alone certainty, of abstract entities is real enough. And some elements of his proposed solution have been part of the prevailing theory of knowledge ever since. In particular, the core idea that mathematical knowledge and scientific knowledge come from different sources, and that the special source of mathematics confers absolute certainty upon it, is to this day accepted uncritically by virtually all mathematicians. Nowadays, they call this source mathematical intuition, but it plays exactly the same role as Plato's memories of the realm of forms, end quote. Yes, there we go. So, in mathematics, it's thought, well, once you've proved something, you can't possibly have made a mistake there because it's proven. And if all the mathematicians converge on the fact that this indeed is a proof, well, then that's the end of the story. On the other hand, the scientist is always open to, as David just said earlier, the new upstart coming up with a theory tomorrow that's going to overturn whatever grand theory you've had your faith in for the last few generations, let's say. That's always a possibility. But no one's going to come along tomorrow with a disproof of Pythagoras' theorem. It's proved in 300 different ways, that's it. We get that from mathematical intuition. It's absolutely certain. Now, of course, David is putting this argument in its strongest form so that he can show you it's flawed. We'll get there. Might not get there today, but we'll get there eventually. Let's keep going. David says, quote, "There have been many bitter controversies about precisely which types of perfectly reliable knowledge our mathematical intuition can be expected to reveal. In other words, mathematicians agree that mathematical intuition is a source of absolute certainty, but they cannot agree about what mathematical intuition tells them. Obviously, this is a recipe for infinite, unresolvable controversy. Inevitably, most such controversies have centered on the validity or otherwise of various methods of proof. One controversy concerned so-called imaginary numbers. Imaginary numbers are the square roots of negative numbers. New theorems about ordinary real numbers were proved by appealing at intermediate stages of the proof to the properties of imaginary numbers. For example, the first theorems about the distribution of prime numbers were proved this way. But some mathematicians objected to imaginary numbers on the grounds that they were not real. Current terminology still reflects the old controversy, even though we now think that imaginary numbers are just as real numbers. I expect that their school teachers have told them they were not allowed to take the square root of -1, and consequently they did not see why anyone else should be allowed to. No doubt they called this uncharitable impulse mathematical intuition, but other mathematicians had different intuitions. They understood what the imaginary numbers were and how they fitted in with the real numbers. Why, they thought, should one not define new abstract entities to have any properties one likes? Surely, the only legitimate grounds for forbidding this would be that the required properties were logically inconsistent. That is essentially the modern consensus, which the mathematician John Horton Conway has robustly referred to as the mathematicians' liberation movement. Admittedly, no one has proved that the system of imaginary numbers was self-consistent, but then no one had proved that the ordinary arithmetic of the natural numbers was self-consistent either, end quote. So, even to today, the terminology is confusing. Calling them imaginary is silly. They're not imaginary. They're just as real as real. It's just a quirk of history. Today, although the word imaginary is still used for, the square root of any negative number, -1 is I, the square root of -2, -3, and so on, we more often talk about complex numbers, which is the superset of the real numbers. The real numbers are just a subset of the complex numbers. The complex numbers are written as A plus IB. A plus IB, where the IB is the imaginary part. And so you can... But A is the A and B are real numbers. And so you can write down any real number as a complex number. But your B will be 0, that's all. And complex numbers with imaginary parts are used in physics all over the place. They're used in electrical engineering, for example, and quantum theory, among many other places as well. So yeah, it's just a misnomer, and it's unfortunate. Because people really do think that just because we've called them imaginary numbers, that therefore that means they really are imaginary, not real. No. But this debate goes all the way back to Pythagoras himself. Like some Pythagoreans purportedly, so the rumor goes, refused to accept irrational numbers. Again, another poor term, rational and irrational. But in this case, rational means can be written as a fraction, okay? P over Q. 1 over 3 is 0.3 recurring. But the square root of 2, okay, which is the length of the hypotenuse of a right-angled triangle where the two isosceles right-angled triangle, where the two sides are 1 and 1, like this, well, the length of that hypotenuse is the square root of 2. And the square root of 2, the decimal expansion, goes on forever, where the numbers don't repeat. And so this is the first such irrational number. People thought those weren't real. So we go through these periods in mathematical history where people deny the reality of certain abstractions, certain numbers. Okay, let's keep going. We'll read just a little more and we'll call it a day here. David goes on to say, quote, "There were similar controversies over the validity of the use of infinite numbers and of sets containing infinitely many elements, and of the infinitesimal quantities that were used in calculus. David Hilbert, the great German mathematician who provided much of the mathematical infrastructure of both the general theory of relativity and quantum theory, remarked that the literature of mathematics is glutted with inanities and absurdities which have had their source in the infinite." End quote. Some mathematicians, as we shall see, denied the validity of reasoning about pure infinite entities at all. The runaway success of pure mathematics during the 19th century had done little to resolve these controversies. On the contrary, it tended to intensify them and raise new ones. As mathematical reasoning became more sophisticated, it inevitably moved ever further away from everyday intuition. And this had two important opposing effects. First, mathematicians became more meticulous about proofs, which were subjected to ever-increasing standards of rigour before they were accepted. But second, more powerful methods of proof were invented, which could not always be validated by existing methods, and that often raised doubts as to whether a particular method of proof, however self-evident, was completely infallible. End quote. And so there we have the first hint here, that even within mathematics, once the mathematics becomes sufficiently complex, hard for people to follow, how can you have absolute certainty that an error hasn't crept in somewhere? Sure, people can look at trivial examples in 1 + 1 = 2 and go, how could it possibly be otherwise? And then you slowly argue your way up. How could it possibly be otherwise that Pythagoras' theorem is correct? Or that pick a prime number is indeed a prime number. Many of these prime numbers, by the way, the really big ones, are only known to be prime because some computer tells us that it's prime. Could the computer be making a mistake? Who knows? But when you get into, Andrew Wiles proved Fermat's last theorem. Like the proof by Wiles is 129 pages long. 129 pages of dense, difficult mathematics that only a few mathematicians in the world can really understand. So, is there a chance there's an error there? Well, now we think no, but of course there's always a chance that people can be making mistakes. So once you get to these kind of proofs, then what you're doing really is you're relying upon explanation, the critical method. If the experts are all saying, well, look, we can't find any error herein, then, for the time being, we accept that this is indeed a valid proof, as we do in science. But that doesn't mean that it can't possibly be overturned. It could be overturned. Unlikely. There's no reason to presume that it's going to be overturned. In the same way, there's no reason to presume at the moment that general relativity is going to be overturned. It could be that the quantum theory is going to be overturned in some way, incorporated within the general relativity in some way, shape or form. I don't know. These are things we don't know. But whatever the case, it isn't the case that mathematics leads to infallibility. Even there, we don't get absolute certainties. Even there, we're conjecturing our way to better explanations of mathematical reality. We're dealing with abstractions, things that aren't bound by the laws of physics, but our methods of proof, including what we're doing with our minds when we do mathematics, is indeed bounded by the laws of physics. That will do for now. Until next time. Bye-bye.